All right, so let's now talk about conservative vector fields, or talk more about conservative vector fields. So you talked about it a little bit before. So what were conservative vector fields? So a conservative vector field, F, is a vector field that is a gradient of something. We say gradient of a function phi, right? Where phi is some function, and we take its gradient. It's going to be a vector field. So a conservative vector field is a gradient of something. This field is called the potential, and sometimes, as we said last time, we take, in physics we take minus the gradient of the potential, but it's really the same thing. It's just the gradient of minus potential. It just means, are you taking phi or minus phi? What are you calling your potential? As far as the mathematics is concerned, it doesn't really matter. Physicists like to talk about minus phi as the potential. All right, so what we want to do is figure out what does being conservative mean. I mean, well, it means this, but maybe that's not so useful. It's really something about integrals of vector fields. And by the way, I noticed that at some point they must have changed the notation in the book on me, because when I did my notes originally, this was the first edition of Rogowski, and they used the DS, which is fairly standard, but I guess they're now using DR, so which is also fairly standard. So they're using, maybe let me write it over here. If I had a curve C, the book is writing DR instead of DS, right? So it's the same thing. And the reason why they're doing this is because they're using R as the parametrization, right? And I was using C as the parameterization. It doesn't really matter. It's just different letters, right? So I guess this was the first edition was using this, and I thought I was using the same as the book, but I noticed that it's now different. Anyway, so let's come back to conservative vector fields. So really, what conservative vector fields are, and this is the way that we want to think about it. And this is a theorem. This is the way I write theorem. As mathematicians, we write lots of theorems, so we make it short. This path independence, right? So suppose that, and I'm going to use their notation. So suppose that R parameterizes a path C from let's say point P to point Q, right? So there's P, there's Q. We're going in this direction, right? So R of T, is giving you positions along this curve, right? Then if F is a conservative vector field, meaning it is a gradient of something, then what we have is that if I integrate along C, this vector field F, right, then this is just the potential evaluated at the final point Q minus the potential evaluated at P. Now, maybe it's instead of saying path independence, this is just the fundamental theorem of calculus for these for vector fields that are gradients, right? But it also says that it's path independent, right? It doesn't really matter how I went from P to Q. R didn't really matter, right? As you know, how I parameterize this thing. I could have gone, you know, some funky way, right? As long as I started at P and ended at Q, then this integral would have been this, right? Now, of course, I need to have that phi, right? Now, in particular, if P is equal to Q, so if it's a closed path, right? If it starts somewhere and ends at that point, right? It's you know, maybe P is equal to Q, right? So the path goes somewhere and comes back. Then, of course, the integral, and this is actually an important case, the integral is 0, right? How does, you know, this is basically equivalent to this. How does that really work? Well, it really works is if I have two paths from P to Q, well, I could go first there by this path and then back by the inverse of this path, right? And saying that the integral around this closed loop would then be 0 is the same thing as saying that the integral along this path is the same as the integral along this path, right? So that's why it's also path independence, and that's why it can be stated either like this, so for closed loops, or it can be stated as basically the fundamental theorem of calculus. Now, of course, you know, fundamental theorem of calculus for vector fields, it doesn't apply to every vector field. Only vector fields that have an antiderivative, and not all of them have an antiderivative. Only the conservative vector fields do. Now, maybe let's look at how it really is the fundamental theorem of calculus, because it really is. So suppose that I have this R of t, and t is between a and b, right? So therefore, what is the integral? Sorry, f dot dr, right? What is this thing? Well, by definition, that's just f r of t dot r prime of t dt, right? Now, this f, this was a gradient vector field, a conservative vector field. So I can just write it as the gradient of phi evaluated at r of t. Right? The same thing. Now, this thing, we've already seen something like this before. That's just the derivative. That's just the derivative of phi with r plugged in. Well, so that's exactly, you know, now this is just fundamental theorem of calculus. This is just a function of t, right? We're differentiating it and then we're integrating it, right? So this is phi evaluated at well, where the curve ends, right? This is the q, right? Minus phi evaluated at where the curve begins. This is p, right? Yeah. So it really is just fundamental term of calculus. Let's maybe do a short example, you know, just to make sure that it really works. let's suppose that we have our f is 2x plus y, 2x plus y, x, right? And if you look at this and you follow the what we did a couple of lectures ago when we were finding the antiderivatives, so you integrate this with respect to x, then you differentiate with respect to y and see if you can make it x, right? You will find that phi is x squared xy, right? Maybe actually, just for completeness, let's do this. So if we have if I have whatever phi is supposed to be, it's supposed to be so f1, right, is supposed to be the partial of phi with respect to x, right, and that's supposed to be 2x plus y, right? That means that phi has to be, well, that's some x squared plus xy plus now some constant, so we call it c, but this constant could depend on y, right? Because for each, this is integration for each fixed y. And now if I do with respect to y, I just get x plus c prime y, and well, I'm supposed to get, this is supposed to be f2, right? And so I can actually just make c so that c prime is 0. For example, I could just take c is equal to 0, right? I could take c is equal to any constant, actually. C could be 1, right? I mean, there's different phis that will work, right? Different potentials that will work. If you think about this this theorem over here, it's the only place where the potential really matters when I take the difference of the potential between 2 points, right? So the absolute value of the I don't mean the absolute value, the actual value, right? Of phi is not important. It's really the difference between 2 points. That's why you when you measure voltage, you take your 2 probes and you put them in 2 different points of the circuit, right? And it tells you what's the difference in the electric potential, right? That's that's the difference in voltage. That's what's important, right? Not some actual number, because well, really, it's only the difference. Anyway, so we don't have to take all the possible antiderivatives. Just one is fine, right? So now the gradient of phi is f, right? And let's suppose that we take our p is going to be 0, 0, and q is going to be 1, 1, right? And let's go from p to q in 2 different ways. So let's suppose that I have r1, which is going to be, it's just going to be t, right? And here t is going to be between 0 and 1. This is just the straight, this is p, this is q, it's just a straight line, right? Now here I can also do another one. I can go from p to q as maybe as sort of a parabola, right? Maybe like this, right? So this is R1 is the straight line, and R2 is going to be this part of the parabola, and this is going to be t squared, right? Again, when t is, so again, this is the same same as before, from 0 to 1. When t is 0, I get 0, 0. When t is 1, I get 1, 1. Right? All right. So let's try to integrate. right? So let's integrate along R1, right? F R1. So this is just the integral from 0 to 1 of now I have this is my f, right? So the f let's just do it in using the definition instead of the theorem, right? That's what I'm doing. So 2x, x was t, plus y was t, right? Comma x, x is t, right? Dot, and now I have r prime, right? R1 prime, we're doing over R1. So this is 1 dt, right? So it's the integral from 0 to 1, and it's 2t plus t plus t dt. So 0 to 1 and 4t, right? So this is just 2, right? If I'm doing that right, hopefully I am, right? The integral from 0 to 1 of t dt is 1/2, so 4 times 1/2 is 2. All right, so let's do this along the R2, right? So 0, 1. So now I'm plugging in something different, right? So here is the same f, right? But now I'm plugging in t and t squared, right? So 2x is 2t because x is still t, plus y is t squared. All right? Then comma x is t, dot, now the derivative over here is 1 2t, right? dt. Or in other words, I have so 1 times this thing, so 2t plus t squared plus t times 2t, so 2t squared, right? dt. So in other words, I have 3t squared plus 2t dt, and right, this is so this is the antiderivative of 3t squared is t cubed, of 2t is t squared, right? And t 0, 1, okay, that's just 2. All right, hey, I got the same thing, right? Well, I'd better get the same thing if the theorem is true, right? Well, now let's try applying the theorem, right? I have a phi, right? So doesn't really matter which r. Let me just write r, right? Any r that goes from p to q. F dr, right, is phi at p minus phi at q, right? So I have phi, right? So phi at q minus phi at p. Sorry, it went from p to q, right? So q is the endpoint. So it's phi at the endpoint is 1 squared plus 1 times 1 minus phi at the origin is just I plug in 0, right? So it's smudged a little bit. So 0 squared plus 0 times 0, 0, right? Okay, so it's 1 squared plus 1 times 1, so 1 star plus 1 is 2. All right, we got the same answer in 3 different ways, and that's basically what path independence means, right? I can either compute this this directly, just by plugging in. This is the way I would compute the path integral for any vector field. But if I have a conservative vector field, if I have a potential function, I can do it this way, And this is definitely easier once I have the phi, right? Now, this you can sort of use this in various ways in computations, right? It's not always that this is easiest. Maybe I can't really find the potential easily, but maybe I know that it's a conservative vector field. You'll notice that the first computation was definitely easier than the second computation. Generally, integrals along straight lines are going to be easier than integrals along something more complicated, right? So if I know I have a conservative vector field and I have a complicated path, I might as well compute it along a straight line, right? Or a couple of straight lines. And that might make the computation easier or even possible, right? So, all right. Now, if we look at what the potential gives us, the potential. Let me look at the contour lines of some potential, right? So this is basically where phi is some constant, right? So what does the gradient of phi look like? Well, let's suppose that this was this was a peak, right? So we know that the gradient points uphill, right? So this is the gradient. That's f, right? Right. The gradient of phi, right? These curves are called equipotential curves. Right? They're basically curves, if you think of it as potential energy, where the potential is constant, right? So it's when you're moving along an equipotential curve, the force is not really acting on you, right? The force this is sort of like I was saying if there was no wind and I was running around a flat parking lot, gravity is not really doing the work. I'm doing the work by moving around, right? Or maybe not running around, maybe just a complicated motion, but maybe I have a really well-oiled some wheel or maybe like some sort of a cart with really well-oiled wheels, so there's no there's no friction or anything like that, and as I'm moving that around, gravity is not doing any work on it. All right, because it's moving along equipotential curves, right? And it's and this is again the place where why do physicists insist on the potential being minus phi rather than phi? Is because they want the vector field to go downhill, because sort of, if you want to use your intuition, you want to say it's going, something is going downhill, right? That's where the force will take it. It's potential energy is going down. All right. Now there's another term about conservative vector fields and potential vector fields, and it says that a vector field is path independent if and only if it is equivalent to a vector field, or maybe I'll just say it is conservative. Right? So path independence and conservative are the same thing. If it doesn't really matter how you get from point to point. You really just care about which equipotential curve you ended up on, and that's the same thing as being conservative vector field. So, for example, if the amount of work that it takes to move, if I have a heavy object, I want to move it from the lobby of a building to the roof. If we're ignoring any friction or anything, it doesn't really matter how I go through the building. How I carry it along what staircase. If I take the elevator, it doesn't really matter. The amount of work that it takes to take the heavy object up to the roof is the same. Of course, if I take the elevator is doing the work, and I'm not doing the work. So that's why it's people usually moving heavy objects. You take the elevator, but something is doing the work, right? It's not free, right? If you have no electricity and the elevator is not working, then you have to do the work, right? But the amount of work doesn't matter. It's only the difference in the potential, right? In that case, in terms of the gravitational potential. Okay, let's maybe say a little bit about really why is it called conservative, right? And it's really because there's something being conserved, right? So in physics, we have that if an object is moving, then the kinetic energy plus the potential energy is constant, right? Conservation, I think there's an S missing. The conservation of energy, right? As if I'm moving along some, I'm moving along some path, or some particle is moving, the sum of the kinetic energy and the potential energy is always constant. It can, each one of these can change, but their sum is constant, right? This is the in an introductory physics class, right? This is if you have a pendulum, right? You look at when do you have when the pendulum is all the way in the center, it's right. It's swinging like this, right? So when it's like this, the potential energy is at the minimum, and the kinetic energy is in the maximum. And as it's going up here, the potential energy is at the maximum, and its kinetic energy is zero, right? Because it's not moving at all as it just on that when it changes direction, right? All right. So the potential energy is that's the potential. Except we're gonna follow the physicists, and we're gonna write this is a minus, right? The force is minus the gradient, right? Of the potential, right? Okay. So now, this at any point, this is potential energy, right? And this is this is maybe gravity, right? Perhaps if it's gravity, then if it would be gravity, then the potential should be something like minus k over r, where r is the distance to the center of the Earth, and then f, if I did the computation correctly, would be minus k. Let's suppose it's in 3 dimension x, y, z, r cubed. I think we did that last time, or the not last time. The last time we looked at conservative vector fields. Doesn't really matter. This works for any force field, right? Conservative vector field, right? So, okay. So that's potential energy. What is the kinetic energy? Kinetic energy depends on how the particle is moving, right? And let's call it R of t, just because that's what we did. And so, what is kinetic energy? Kinetic energy, by definition, is 1/2 times the mass, so m is mass of the particle, times the speed squared, right? That's the kinetic energy, right? And it's, you know, the right. Anyway, that's just the definition, right? And well, what the total energy of of this particle is kinetic plus potential, right? And we're trying to show, we want to see why this is conservation of energy. That the total energy is not changing with time, right? So, well, let's look at what E is. Well, let's put the kinetic energy in there. So 1/2 m r prime t squared, right? Plus potential energy, so that's phi of r of t, right? That's the total energy of this particle, right? Now, there's a couple of things. First, what is this? This is I can write this thing as just r prime r prime of t dot r prime of t, right? That's just the magnitude squared is just the dot product, right? Plus phi of r of t, right? So this is actually not that hard to differentiate because of the square. There's no square root, right? So so this is E, right? So let's figure out what's the derivative of E with respect to t, right? Well, now if if you remember from when we were doing calculus was the dot product, they still had the product rule, right? So this was 1/2 m r double prime t dot r prime of t plus 1/2 m r prime of t dot r double prime of t, right? And now we have to, now we come to the potential, and when we differentiate, where's the chain rule, right? So it's the gradient of phi at r of t, right? Dot r prime at t. All right. Okay. Well, let's we'll need another page, but maybe, because I want to point to this, I want to get rid of this page just yet. If you look at these two terms, right, they're almost the same. It's just that the r prime double prime is here and r prime is here, but the dot product is commutative, right? So this is the same thing as if I put r double prime over here, right? And I have this 1/2 then disappears, right? I add up two terms that are the same guy. So that means that let me rewrite that over here. The derivative with respect to E of energy is m r double prime of t dot r prime of t, right? And then plus we had the gradient of phi. Well, this was the F. This was the force, right? Evaluated at r of t, right? Dot r prime of t. Okay. All right. Now we do a little bit of algebra, and we have mass r double prime plus F evaluated at r of t. Let me just not write that. It's evaluated where it's evaluated. This is evaluated where it's evaluated. Dot r prime, right? I'm just not writing where these things are evaluated, right? That's wherever it makes sense. That's time t. Now, what is this, right? this is mass. Oh, sorry. I was thinking this is where I forgot the minus sign. I'm not a physicist, right? I was thinking that that's not working out, right? We had F was minus the gradient of the potential, right? That's where the minus sign is important, right? Otherwise, we'd have to put the minus sign somewhere. You have to put it somewhere, basically. So it's minus. Sorry about that. Now, I have Newton's second law. Mass times acceleration equals force. I have force, I have mass, I have acceleration. So if mass times acceleration equals force, then this term is 0. So this is 0, right? So that's conservation of energy, right? It just follows from, in this case, from Newton's second law, or vice versa. You could say, well, if we have conservation of energy, we've just derived Newton's second law, right? So either way, right, you get one direction or the other direction, right? So that's really where these things come up in physics, right? And now you've seen the thing that I just missed over here, right? Was that there was the gradient of phi, and I forgot to write down the minus sign, right? You can see where the minus sign is important, because if there was a plus sign, as there was, then I wouldn't get a 0, right? All right. So it's well, it would be just maybe say a little bit more about it. It would just it's not that you can't do the physics without the minus sign. It's just that it wouldn't be the sum of the potential and the kinetic energy, or sum of the potential function and the kinetic energy. You'd have to take the difference. That would be the conserved quantity, right? So physicists like it to be the sum and think of both as energy, right? So think of the potential as the energy, think of the kinetic as the energy, and so so then with the negative sign, you don't have to put the negative sign in the other place, right? All right. So that's it for today.